Section 5.1 talks about eigenvalues and eigenvectors. Eigenvalues and eigenvectors. So first thing, of course, we start by defining what is an eigenvalue, what is an eigenvector, right? So let's start with an eigenvector. So an eigenvector, which is one word, of a n by n matrix A is a non-zero. It can be zero. It's a non-zero vector x, so that ax is lambda x. Ax is lambda x for some, so that's a Greek letter lambda, for some scalar lambda. So what is this lambda? This lambda is called the eigenvalue. Lambda is called the eigenvalue of A. We call the eigenvalue of A under some condition I will state in a minute. So what is this equation saying? You have a square matrix A, you multiply it by x. The output is a multiple of that x. So lambda is a scalar, so the output is a multiple of x. So if that's the case, then x is an eigenvector for the matrix A. That's what this equation is saying. Take a matrix, multiply it. It's kind of like a transformation here. So that's a transformation. Take a matrix A, multiply by x, and if you get a multiple of x for some scalar lambda, then x is called an eigenvector, which can be zero. So x cannot be zero. Called eigenvector. And lambda, in this case, we called an eigenvalue for the matrix A if there is a non-trivial solution x of the equation ax equals lambda x. If this equation has non-trivial solution x, then lambda is called the eigenvalue. Let's look at an easy example. Is this vector 1, negative 2, 2 an eigenvector? An eigenvector of the matrix 3, 3, 5, 6, 3, 6, 7, 7, 5. Is this an eigenvector? So they're not asking you to find the eigenvector. They're just asking, is this an eigenvector? And how do we prove this or disprove it? So to do so, we ask ourselves, if I take A and x, do I get a multiple of x? Well, let's see. I'm going to take matrix A. And I've multiplied by 1, negative 1. What do I get? To multiply this, you multiply row by column. 3 times 1, 3. So you have a 3. 6 by 2 minus 12. 7 by 1, 7. Row by this column. 3 by 1, 3. 3 by 2 minus 6. 7 by 1, 7. Next one. Row by column. 5 by 1, 5. 6 by 2, 12. And 5 by 1, 5. Let's see what we get. 3 plus 7, 10. Minus 12 is 2. 1 plus this is 4. 10 minus this, negative 2. But for this last vector, I can factor a 2 out. Right? Actually, there's a negative 2 there. Factor a negative 2 out. That will give me 1, negative 2, 1. So this is basically negative 2 times the vector x itself. So since ax is a multiple of x, this tells us x is an eigenvector of A. Note, lambda is -2 in this case, is the eigenvalue. Let's move on with how about if we are asked, is negative lambda equals -2 an eigenvalue of the matrix 7, 3, 3, -1. Okay, is this an eigenvalue? Well, remember how we defined the eigenvalue up here. We defined lambda to be an eigenvalue of a matrix A if there is a non-trivial solution x for this equation, ax equals lambda x. So again, we can apply that here. We say lambda equals -2 is an eigenvalue, okay, eigenvalue of A if and only if. 2 F's means if and only if. 2 F's is not like wrong spelling. This means you can go both ways. So if this implies that, or if that implies this, so you can go both ways. If and only if ax equals -2x, because lambda is -2, has a non-trivial solution. Non-trivial solution. Okay, it has non-trivial solution. So in order for this to happen, let's say we can basically rewrite this in this format. So ax plus 2x equals 0. Now when I factor an x out, this x is not an algebraic x, this is a vector x. So this is a vector x. So when you want to factor a vector x out, the way it works, you do a plus 2i. I is the identity matrix, not just 2. Okay, so what I'm gonna do here, I'm gonna compute this one first. Compute a plus 2i. A is the matrix 7, 3, 3, -1 plus 2 times the identity matrix 1, 0, 0, 1. And what do we get for this? 9. Let's see. 7 plus 2, 9. 3 plus 0, 3. 6 plus 0, 6. No, 3 plus 2 is 3. -1 plus 2, 1. Notice the first column is the 3 times the second column. So we say since the columns of A are linearly independent, dependent, then A plus 2ix equals 0 has a non-trivial solution. So we say -2 is an eigenvalue of A. Note, recall the null space. Null space is, of course, it's a fundamental space in a matrix. So a null space is a fundamental space in a matrix. Is basically the set of all vectors which end up as 0 when transformation is applied to them. In other words, it consists, the null space is consists of all vectors x such that ax equals 0. So this x cannot be 0. So in this case, we say the set of all solutions of a minus lambda I, remember how we had 2 here, or negative 2x equals 0, is the null space of the matrix, null space, not matrix A, but A minus lambda I. This is a subspace. So always the null space is subspace of Rn, and it is called, has a specific name, it's called the eigenspace. You know how we have eigenvectors, eigenvalues, that's called eigenspace of A, of matrix A corresponding to lambda. Corresponding to lambda. So what does the eigenspace consist of? We say the eigenspace consists of all eigenvectors corresponding to lambda and the zero vector. So if you take the set of all the eigenvectors corresponding to lambda and the zero vector, that gives you the eigenspace. The question we're going to answer today, how to find a basis for the eigenspace. So how do you find the basis for the eigenspace? Let's do this by providing you with an example. I have this example, a matrix 10, 4, negative 9, negative 2, and lambda is 4. So what do? We find the matrix A minus lambda I. A is 10, 4, negative 9, negative 2, minus lambda, which is 4 times I. You know, it's 1, 0, 0, 1. That's the identity matrix. So 10, 4, negative 9, negative 2, minus, multiply the 4 in, 4, 0, 0, 4. And if we subtract them, if we subtract these two, what do we get? 10 minus 4 is 6, negative 9, 4 minus 0, 4, and negative 6. So what do? We take A minus lambda I x equals 0, and this would be 6, 4, negative 9, negative 6, 0, 0 equals, or not equals. We're going to write this in echelon form, and I'm sure everyone can do the echelon form for this. So when I did the echelon form, I got 1, 0, negative 3 halves, 0, 0, 0. And you know, this is all zeros here. So if I look at the first row, I have 1x1 minus 3 halves x2 equals 0. So x1 is 3 halves x2. So then the column x1, x2, the vector, x1 is 3/2 x2, and x2 stays the same. You can factor x2 out. That gives me 3/2 and 1. 3/2 and 1. So we say the basis for the eigenspace is 3/2, 1, or if you see different answers in the back of the book, if you're solving a problem, you can multiply by 2, or you can factor 1/2 out, so that will give us 3 and 2. We continue now. One thing we need to learn here is how to find the eigenvalues for a given matrix. For the meantime, we introduce a theorem, and then in the next section we have more tools for you to find eigenvalues. But in this theorem, we say that the eigenvalues, to find them, the eigenvalues of a triangular matrix, this is only deals with triangular matrices. Triangular matrix are the eigenvalues are the entries on its main diagonal. It's on main diagonal. So if you have triangular matrices go like this, and then everything is 0 here, or they have you have entries here and 0 above the main diagonal. So the main diagonal, this is the main diagonal, this is the main diagonal. So those entries on the main diagonal, those will be the eigenvalues for that matrix. As an example, find the eigenvalues of the matrix 0, 0, 0, 0, 5, 0, 0, 6, -3. So notice, is this a triangular matrix? Yes, it is. What are the entries on the main diagonal? This, this, and this. So the eigenvalues for this matrix are 0, 5, and -3. That's the easiest one to find the eigenvalues for triangular matrices. This is the easiest thing to do. I'm going to write another one, and you try it. I remember when I took the class, the professor used to ask us to find the eigenvalues. Sometimes we don't see them on the exam. We don't see it right away. Or sometimes what you have to do is one operation, one row operation, like you maybe multiply one of the rows by something added to the next row to clean up, to make it triangular. Then the eigenvalues will be basically the entries on the main diagonal. So let's do this one. As you can see, this is a triangular matrix again. So the eigenvalues are 8, 0, and -9. Question someone asked, can the eigenvalue be 0? The answer is yes, but not the eigenvector. Yes, but not the eigenvector. Okay, it can be 0. And I can add a note here, if the eigenvalue of matrix A is 0, then this tells us AX equals 0x, right? Or 0. So this is the set of vectors. So the vectors with, we say the vectors with eigenvalues 0, with eigenvalue 0, make up the null space that I spoke about earlier, right? Space of matrix A. matrix A. Now we may move on and give more questions about this. About, this section is just an introduction to eigenvalues and eigenvectors. Let lambda be an eigenvalue of an invertible matrix A. Invertible matrix A. Show that that's like a proving problem. Lambda to the -1, like lambda inverse, is an eigenvalue of A inverse. We're going to split you in groups to have you work on this. Invertible matrix, what does that mean? That means the determinant cannot be 0 of matrix A. So they said lambda is an eigenvalue. Lambda an eigenvalue means AX equals lambda X. Show that lambda inverse is the, what does that mean? We need to prove that A inverse X equals lambda inverse X. That's what we need to do, right? So since lambda is an eigenvalue of A, this means there is a non-zero vector X, so that AX equals lambda X. Okay, so AX equals lambda X. Since they give us A is invertible, means the determinant is not 0, then we can multiply both sides of that equation above by A inverse, right? Keep an eye on what we need. We need this. So A times A inverse, I can rearrange this like that, and I can bring the lambda out as a scalar. A inverse times A is the identity matrix, so this is gone. X equals lambda A inverse X, like that. Watch something here. So this is what I need. There's no lambda inverse here. So notice, since A is invertible, this is not 0, right? X, we told you, is not 0. This X is not 0. So this tells us that lambda is not 0, right, for this equation. Since it's not 0, then we can multiply both sides by lambda inverse. Lambda A inverse X. Lambda inverse lambda is nothing, just 1. So we get lambda inverse X equals A inverse X, which can be rewritten as A inverse X equals lambda inverse X. And that's what we are required to prove. Any questions about this?